I would like to do one more of those style of problems, a little bit more challenging maybe. Let's take a look at this piecewise defined function. F of x equals, let's say that for the first option, it's x squared minus 4 over x minus 2. That's whenever x is strictly smaller than 2. It's equal to ax squared minus bx plus 3 whenever x is between 2, inclusive, and strictly less than 3. And finally, it's equal to this linear function for x bigger than or equal to 3. And the question is this. Notice here we have two parameters, a and b, right? In the last question, we just had one parameter, that's c. But this time we're going to have to find two values, a and b. So for what values of a and b will f be continuous everywhere? Maybe instead of everywhere, maybe I should say on R. Notice that all of these functions, like this is a quadratic, so it's continuous everywhere. Like it's a polynomial, so it's continuous everywhere. Similarly, 2x minus a plus b is a polynomial, so it's continuous everywhere. And this here is a rational function. We didn't mention it yet, but it's any rational function is continuous as long as the denominator is not 0, right? Remember that limit theorem on rational functions? That we can do the limit just by putting in the number as long as the denominator is not 0. So what I'm trying to say is this. Whenever you have a piecewise function, do you see these transition numbers? It's like the graph is something, and then at 2 it changes, right? To something else. And then over at 3 here, it changes again, right? To I guess, a line. Now, our goal is to make these graphs all match up nice, right? Maybe if I choose my numbers a and b really well, maybe I can make it so these graphs kind of perfectly match up nicely. I guess this needs to be a little bit longer, but you get the idea, I hope, right? What value of a and b is going to make these three pieces all connect nicely together? Well, let's do it. We first it's kind of like two of the same kind of problems we just did. We first do the problem at 2, because 2 is our first transition point. And then we do the problem at 3, okay? And that's the idea. So let's see how this goes. So at x equals 2, I'm going to work, say, over here, okay? And for x equals 3, I'm going to work over here. What was the first thing we should check? We should check the function value, okay? So what is f of 2? Which one of these three options do I use if I want to evaluate f of 2? Well, looking over here, I see that when x is greater than or equal to 2, in particular when x is equal to 2, I should use this middle option. So I'm going to put 2 in for x there and see what I get. 4a minus 2b plus 3. Why don't I write that below? All right. The next thing to do is to find the, you know what? Since I kind of out of room, I'll do the 3 stuff below the work I'm doing right now. Okay. That way I can write this all in one shot. So we know what f of 2 is. Good. Well, what I go like this. Now let's do the limit. Let's do the two limits, okay? We need to find the left and right limit at 2. Those are the next things we're going to calculate. Now, the way we do this is that we remember that whenever we do a right or left limit, we kind of know where x is. If x is going to 2 from the right, that means x is a little bit bigger than 2. And since it's just a little bit bigger than 2, we can certainly assume it's smaller than 3. So that means we should be using this middle option, ax squared minus bx plus 3. This is the limit of a polynomial, and we know that to do such a limit, all we have to do is take that number and put it in for x. And I get the same thing as actually I got over here, right? And that happens often. So get used to that. So this is going to be 4a minus 2b plus 3. But I bet you the answer on the next one is going to be more interesting. Let's see what happens. When I do the left limit there, here x is below 2, right? So I'm going to be using this option, x squared minus 4 over x minus 2. Now, here's where we have to be careful. Can I put 2 in this limit and just get the answer? Well, this is a rational function. And remember, to do the limit of a rational function, all you have to do is put the number in. But that is only true when the denominator is not 0. When I put 2 in the bottom, I get 2 minus 2 is 0. So this is out of 0. So that means that this is an indeterminate form. I'm going to have to think about this a little bit more. This form is actually 0 over 0, so maybe I should try factoring, right? We've done this kind of a limit many times before. So I'll factor the top as a difference of squares. And when I do that, I see some nice canceling that happens here. So it looks like this limit is really the same as the limit is just x plus 2. And now we're back to the limit of a polynomial, so I can just put that in. And I get 4. So the 3 quantities that I get here are the 4a minus 2b plus 3 and 4, right? So in order to be continuous at 2, we need that these 3 quantities to be equal. Obviously, the 4a minus 2b plus 3 is the same on both. So we need that basically 4a minus 2b plus 3 be the same as 4. And as long as that's true, I'm guaranteed to be continuous at x equals 2. Now, this equation has 2 variables. This is one equation and 2 variables. You cannot solve that equation for a and b explicitly as unique numbers. So I think what we should do is do the same kind of analysis, but this time at the other transition point, namely x equals 3. So we're going to do the same kind of thing now, except at x equals 3. First of all, what is f of 3? Let's see. F of 3, I'm going to be using the bottom option. So it's going to be 2 times 3 minus a plus b. 2 times 3 minus a plus b. Which is the same thing as 6 minus a plus b. All right. So that's the value at 3. Now let's calculate those limits. We need to calculate the right and left limits and see what they are. When I do the right limit at 2, oops, sorry. We're not working at 2 anymore, are we? We're working at 3. So when I do the right limit at 3, let's see. The right limit at 3 means x is bigger than 3, so I'm going to be using this option again, 2x minus a plus b. And again, that works out to be the same as this, right? When I plug 3 in this polynomial, I get 6 minus a plus b. This next one is going to be the one that's going to give us information. When I do the left limit at 3, I would be using the middle formula, right? Because when x is a little bit smaller than 3, I should use this ax squared minus bx plus 3. So ax squared minus bx plus 3. To do this limit, it's simple because this is a polynomial. We just put it in. And let's see what we have. We get 9a minus 3b plus 3. We need that these 3 quantities be the same, which is the same thing as saying these 2 quantities have to be the same. So Our reward for this work, for our analysis at x equals 3, is that we need that 9a minus 3b plus 3 be the same as 6 minus a plus b. Now, these are our two equations we need to work on, okay? We now have two equations in two variables. This one and this one. That's a system of equations in two variables. We can solve that. How about I recopy these? Let's say go like this. And this is what we need to solve now, okay? This is the end of the problem now, kind of. But we still need to solve this system. So this is our first equation. And our second equation is right here. Why don't I just write it down? 9a minus 3b plus 3 equals 6 minus a plus b. All right. How do we solve this? Well, why don't we clean it up first? Let's line up the a's and b's, and let's bring all the numbers to the other side. For this first one, I'm just going to recopy the 4a minus 2b. But I'm going to bring this plus 3 to the other side. It becomes a minus 3. 4 minus 3 is 1. So the first equation looks like that. For this one here, let's bring the a's together. I have a 9a over here, and I have a minus a here. When I bring the minus a to the other side, it becomes a plus a. 9a plus 1a is 10a. Here, for the b's, let's see. Minus 3b minus b is minus 4b. And let's bring this 3 to the other side, so we get 6 minus 3, which is 3. And there's our system, right? Do you remember how to solve something like this? There's different ways of doing it. I kind of would like to do this. So why don't I multiply this one by, say, 2? Or even negative 2. Let's see. And this one I'll just keep the same. In other words, I multiply by 1. So this one doesn't change. But this one's multiplied by negative 2, and I'll explain in a second why I chose that. Negative 2 times 4 is negative 8a. Negative 2 times negative 2 is positive 4b. And 2 times negative 2 times 1 is negative 2. And what I'm going to do now is I'm going to add these, okay? Notice the 4b and the minus 4b, when I add those, they cancel each other off. If I would have multiplied by 2, I would have had a negative 4b here, and I would have had to subtract. That would have been perfectly fine as well. I prefer to add, though. I think it's a little bit more natural. So that's the reason I chose negative 2 as opposed to positive 2. If I would have chose positive 2, I would have had to subtract. But I prefer to add, so I chose negative 2. What is negative 8a plus 10a? That's 2a, right? And this is like 0, so I don't even have to write it. And 3 plus negative 2 is 1. And so 2a is equal to negative 1. So that means that a is a half. We've just found a. So a is a half. All right. How about b? Well, since we know what a is, we can just plug a into one of these formulas and work it out. So why don't I take this first equation, 4a minus 2b equals 1. But instead of writing a, I'm going to write what a really is. A is a half. And this gives me a little algebra equation in b. I can solve that. 4 times a half is 2. I'll leave the minus 2b there. I'll bring the 1 over. I'll bring the 2 over. So it's 1 minus 2, which is negative 1. So b is negative 1 over negative 2. But that's the same as positive 1 over 2. So let me actually just... I'm just being picky here. Let me write it like this. So b is equal to 1 over 2. Those are our two answers, okay? So we finished this problem. So this is our answer, okay? We need a equals 1/2 and also b equals 1/2 for f to be continuous everywhere. Or in other words, on R. So I hope that makes sense. That's the answer for this one.